curious, looking up. When a raindrop detaches from a high-altitude cloud, it has a long way to go. It's starting a journey from thousands of feet up, with Earth's gravity pulling it down every inch of the way. Because of gravity, that drop experiences constant acceleration. In a true vacuum, it would be gaining speed every single second it spends in freefall. If that acceleration went unchecked for the entire descent, a standard raindrop would hit the ground traveling at the speed of a bullet. A light drizzle would be completely lethal. But when a raindrop actually hits your umbrella, it's a gentle tap. Somewhere mid-flight, the drop's acceleration drops to exactly 0, locking it into a safe, constant cruising speed for the rest of the trip. The air between the cloud and the ground acts as a fluid, exerting a force that fights back against gravity. To understand how objects move through our world, we have to look at the mechanics of this resistance. To see exactly how fluids fight back, we need to strip away the complex weather of the sky and look at a clean laboratory model. Imagine dropping a solid metal sphere into a tank of fluid. Right away, there is a constant downward force at play. This is the pull of gravity based on the sphere's mass, which we call its weight. At the same time, the fluid itself is pushing upward against the sphere. This is buoyancy, the exact same force that keeps a boat afloat on a lake. But for a dense metal sphere, or a heavy raindrop, the downward weight is much stronger than the upward buoyancy. The net force is still pointing down, so the object starts to accelerate. In the 19th century, English scientist Sir George G. Stokes quantified this interaction by defining the specific mathematical laws governing fluid friction. Stokes observed that as a body falls through a fluid, it drags the adjacent layers of that fluid along with it. This relative motion between the moving object and the surrounding fluid creates a strong retarding force known as viscous drag. We can see exactly what generates this drag by looking at Stokes' law. This equation shows that the drag force relies heavily on physical traits, specifically the viscosity, or thickness, of the fluid, and the radius, or size, of the sphere. But the most crucial variable in the equation is v, velocity. The drag force is directly proportional to how fast the object is moving. This means viscous drag is an entirely reactive force. Gravity and buoyancy stay constant, but the faster that sphere falls, the harder the fluid fights back. Let's bring this back to our falling sphere. As it begins to drop, we get a new upward arrow representing viscous drag. Because the sphere is still accelerating, its velocity is increasing. And as velocity increases, that drag arrow stretches and grows larger. Eventually, the object hits a critical threshold. This is the exact fraction of a second when the growing upward drag, combined with the constant upward buoyancy, perfectly equals the downward pull of gravity. Isaac Newton's laws of motion tell us what happens next. When opposing forces balance out, the net force drops to 0, and with 0 net force, acceleration drops to 0. The object completely stops speeding up. This unaccelerating state of descent is what physicists call terminal velocity. It's the absolute speed limit for an object falling through a fluid. When net forces reach 0, we derive this equation for the exact terminal velocity of our sphere. Isolating the variables leaves two factors dictating the speed limit: object size, as radius squared, and fluid thickness, as viscosity. With these variables isolated, we predict exactly how changing the physical traits of either the object or the fluid dictates its ultimate speed limit. Let's test the radius. We drop two spheres into identical fluid tanks, the right sphere twice as wide. Since terminal velocity scales with the radius squared, the larger sphere has a higher speed limit, easily accelerating past the smaller one. Next, we test the fluid with identical spheres. The left tank holds water, the right holds thick machine oil. Viscosity acts inversely. The oil suppresses the sphere's speed immediately, while it plummets quickly through the water. Stokes' law is the invisible mathematical balancing act dictating all of these interactions. It's the reason engineers can design heavy machinery that operates safely in oil, and it's the exact reason our falling raindrop hits the earth with a gentle splash instead of a lethal impact.